So we come now to one of the more useful techniques involving matrices, and that is to use them to solve systems of simultaneous equations. Unfortunately, the way that you do them in methods isn't actually that useful. It should be, but because of the limitations and time constraints in the course, they sort of teach you a little bit of it, and so it's still it's not going to seem that much better than the way that we did it previously. So the best way to solve equations is still going to just be to use solve on your CAS. So most computer algebra systems actually have matrix-based algorithms embedded in their programming, which allow them to do all the calculations that they do. So a long time ago, we looked at solving simultaneous equations in the following format. So we take two linear equations. This first one here is 6x plus 8y equals 7. And a second simultaneous equation, 2x plus 4y equals 5. We'd label each equation 1 and the second one equation 2. We'd have a look at the coefficients of x. Here we've got 6, here we've got 2. So in order to have the same coefficient of x, we need to multiply equation 2 by 3, multiply all the terms in the equation by 3 to give a third equation. Once we've got the coefficients of x the same, we then went equation 3, take equation 1, taking away like terms, we'd end up with 4y equals 8. Dividing both sides by 4, we'd find y equals 2. Once we had y equals 2, then we'd make a substitution into 2. Substituting y equals 2 into 2, we'd get 2x plus 4, 4 times 2 equals 5. Solving that equation for x, we'd find that x is minus 3, 2. So we'd finally find the coordinates of that intersection of those two lines. Using matrices, it's a little bit better. As I said, there are better techniques, but this is the one that you're going to learn for methods. So another way we can write a system of equations in matrix format is to write a coefficient matrix. So the coefficient matrix just includes the coefficients of x and the coefficients of y. So the top line would be just 6 and 8, and the bottom line would be 2 and 4. We then write the x and y as a vector or another matrix next to that matrix, and we write our solutions as a matrix as well. So we'll call this matrix A, this X, and this B. And again, we call A coefficient matrix. Now let's think about what we've just learnt previously about, or apply what we've just learnt about inverse matrices and see if we can find a way to solve our system of equations using matrices. So what we have here, we have A times X gives us B. So let's just write that as AX equals B. Now what happens if we multiply both sides by the inverse of A? So we multiply this side by A inverse, and being consistent, multiplying this side by A inverse. Now, notice that I have put A inverse out the front on the left-hand side, and I've put A inverse out the front on the right-hand side as well, because the order of multiplication with matrices is, of course, important. Now, what we should notice is that if we have A times A inverse from the previous exercise, we know that A times, or A inverse times A, is just equal to the identity matrix. So we have here the identity matrix times X equals A inverse times B. We also know that if we multiply the identity matrix by any matrix, we just get back the same matrix. So the identity matrix times x is just going to give us x. And we're now left with a way to find a solution for x. So if we have some coefficient matrix or some system of equations, ax equals b, to find the solutions, we just have to multiply our solutions by the inverse matrix of the coefficient, or inverse coefficient matrix. Now be careful also, A must be non-singular, because of course if it is singular, that means that the determinant equals 0, so we won't be able to find A inverse. So this method is only going to work where A is non-singular. It should be a square coefficient matrix. Then we can find the solutions of Ax equals b by finding x equals A inverse times b. So here's an example. So the first step is to write that in matrix form. So we write out the coefficient matrix as we previously did above. So in order to solve this system of equations, we're now going to find the solutions by multiplying A inverse times b, which means we need to find A inverse. So the first thing we're going to do, our first step, is to calculate A inverse. We recall from previous exercise that A inverse is 1 over AD minus BC times that funny rearranged matrix, which is DA minus B minus C. Inserting the correct values in there. So our D is 4, our A is 6, so 6 times 4, which is 24, minus B times C, so minus 8 times 2, which is minus 16. D is 4, minus 8, minus 2, 6. So we might actually multiply that out. So we have 1 over 8 times 4 minus 8, 2, 6. So that's equal to 1/2 minus 1 minus 1/4 and 3/4. So all I've done there is multiply each of those values within the matrix by an 1/8 using scalar multiplication. So now that I have my inverse matrix, the next step is to multiply A inverse times B. Make sure that you have the order correct. So we've got 1/2 minus 1 minus 1/4 times 3/4. And we're going to times that by B, which is 7/5. Now you could do that in your head or you could do it on your CAS. Oops. I keep doing that. Inserting our values, we've got 1/2 minus 1 minus 1/4 minus 3/4. Oh, sorry, 3/4. And we're multiplying that by, don't need to do that, 2 by 2 matrix, and our 2 by matrix was 7, 5. So we end up with minus 1.5 and 2. All right, that is a fraction again. Minus 1.5 is minus 3 on 2 over 2. So running out our solution, we found that xy, our x, is equal to our A inverse times B. And from that we can see that x is equal to minus 3 on 2 and y is equal to 2. So we have an intersection at the point minus 3 on 2, 2, which is the same solution that we found earlier by doing it by the old method. So alas, this is also quite yucky. It's not really much better than what we could do. And of course, this method only works if the determinant of A is non-zero. So if possible, I'd always just use solve on CAS to solve systems of simultaneous equations. Okay, so we should remember that there are 3 possible scenarios for solving systems of 2 equations. So either we have 2 lines that intersect at a single point, so one point of intersection, a unique solution, or we may have 2 lines that have the same gradient, they're parallel, so they'll never intersect, so there'll be no solutions. Or we might actually have 2 lines that are one on top of the other, so infinitely many solutions. So if the determinant of the coefficient matrix is 0, you'll have to compare the x and y intercepts, or the gradients and y intercepts, to determine whether there's no solutions or infinitely many solutions. So an example is just one from the textbook. For the remainder of the matrices chapter, I'll probably keep using the examples from the textbook because they're fairly straightforward. So if you don't like the way that I explain it, have a look them up in the textbook and see if they explain it better. So to solve the following set of equations from this example, so we've got 3x minus 2y equals 6 and minus 6x plus 4y equals minus 12. The first thing we're going to do, of course, is write down the coefficient matrix. So we have 3, minus 2, minus 6, and 4. If we were going to find the inverse of that matrix, we would have to find the determinant, because of course the determinant is the 1 over the AD minus BC. So if we were calculating the determinant of that matrix, so we'd have 3 times 4, which is 12, minus 2 times 6, which is a positive 12. So I'd have 12 minus 12, which is 0. So the coefficient matrix is singular. The determinant doesn't exist. It's singular. There is no inverse. So we can't proceed with the method that I just taught you. So in other words, we are going to have to compare the x and y intercepts. So let's take the first line, which is 3x minus 2y equals 6. Let's find the x-intercept. So we let y equal 0. So in other words, we have 3x equals 6 and we have x equals a half. Then we'll find the y-intercept. Let x equal 0. So we have minus 2y equals 6. So y equals minus 3. Second line was minus 6x plus 4y equals minus 12. Find the x-intercept. Find the y-intercept. And what we see there is we actually have identical x and y intercepts for both lines. So x is a half for both, and y equals minus 3 for both. So as they both have the same intercepts, therefore the lines must lie on top of one another. And our answer is then infinitely many solutions. So you can go ahead now and try the first few questions from 7.5. We'll just do questions 1, 2, 3, and 5. So we'll work now through a longer example from the text. So in this example, you asked to find the values of k for the following two equations that have, and where k will allow the two equations to have a unique solution, no solutions, or an infinite number of solutions. The first thing we're going to do is write down the coefficient matrix. Coefficient of x in the first equation is k. Coefficient of y is minus 3. In the second equation, the coefficient of x is 10, and the coefficient of y is minus k plus 1. Then we're going to find the determinant. A times d, so we'll have k times minus k plus 1. I'm just moving the minus out to the front. And then minus 3 times 10, so it's going to be plus 30. So let's expand that. So we get minus k squared minus k plus 30. Take negative 1 out as a common factor. And now we should be able to factorize that expression. Oops, missed my squared. So factorizing that expression, 6 times minus 5 gives me 30. And 6 plus minus 5 gives me 1. So I can factorize that using k plus 6. K, oops, that's not k. K minus 5. Now what we know is there are unique solutions when the determinant does not equal 0. So we want to know when our determinant does not equal 0. Oops, I want to write it like this. 0 does not equal our determinant. So if we use So if we use the null factor law, that means that k does not equal 6 minus 6, or positive 5. So there are unique solutions. When k does not equal -6 or 5. So that's our answer to part A. Now we've got to find out when there are no solutions and when there are infinite number of solutions. So let's substitute in when k equals -6. So we're just going to put -6 in for k in our first equation and -6 for k in our second equation. So I've substituted k into both of those equations, and I'm just going to simplify them a little. So that top equation, so 1 simplified is going to just be -6x minus 3y equals -7, and the other will be 10x plus 5y equals 8. That's better. So we need to rearrange both equations for y so that we can compare them. This time we're going to be comparing the gradients and the y-intercepts to see if they're parallel or if they're on top of one another. So equation 1, taking the 6x to the right hand side, dividing through by -3, we'll do the same for the second equation, 10x plus 5y, subtracting 10x from both sides, dividing by 5. So what we see is that we have same gradient, but we have different y-intercepts. So if we've got the same gradient, different y-intercepts, then when k equals -6, there are no solutions. The reason being, because they have the same gradient, different y-intercepts, then it must mean that they're parallel, but they're not lying on top of each other, so therefore no solutions. So that answers part B. We could guess then that if we substitute that other value for k that we found earlier, the 5, if we substitute that into our original equations, then we should assume that at that point there must be infinitely many solutions, but we need to still prove that. So for part C, we're going to substitute k equals 5. So substituting k into the first equation, we should get 5x minus 3y equals 5 minus 1. And the second equation, we should get 10x minus 5 plus 1, y equals 8. Again, simplifying those a little so that the first equation becomes, and the second equation becomes minus 6y equals 8. Now, if you look closely at those two equations, it's the second equation here, equation 2. It's just a multiple of equation 1. So equation 2 equals 2 times equation 1. So because we have that, the fact that they're just they're just multiples of one another, then that means that there must be infinitely many solutions because they're in fact the same line. So when k equals 5, there are infinite solutions. So now that you've gone through that, you should be able to try question 7, just the single one question from 7.5. So at the beginning of this exercise, we showed that if we have an AX equals B scenario for solving equations, then we can solve it by multiplying B by A inverse. It can also be shown that if we have some matrix vector X times a coefficient matrix equaling B, that we can solve for X by multiplying B by A inverse. So notice that all that's happened here, X was on the right of A, so we have to multiply by A inverse on the left of B, whereas here, X is on the left of A, so we multiply A inverse on the right of B. Remember, order of multiplication with matrices is very, very important. So why does this happen? So if we have, if we have X, A equals B, and we multiply both sides by A inverse, we have to multiply on the right of A, so that we have our A and A inverse next to each other. So we have to multiply on the right of B. We know that A times A inverse equals the identity matrix. And we know that if we multiply any matrix by an identity matrix, we just get back the original. So that just becomes X. So an example from the textbook just to finish off. So if we're given two matrices A and B, and we have to find a matrix X, one in which we have AX equals B and one in which we have XA equals B. So the first thing we're going to have to do for both of them is to find A inverse. So to find A inverse, we have 1 over AD minus BC. So A is 3 and our d is minus 6, so we have minus 18. Minus 5 times 4, which is positive 20. D is minus 6. A is 3, making B positive and negative. So there we go. There's our inverse. So that's just 1/2 minus 6, 5, minus 4, 3. Okay, so if we do A, we have to do A inverse times B to solve it because we have AX equals B. So then the solution will be A inverse times B. So we have 1/2 minus 6, 5, minus 4, 3 times our B, which is minus 5, minus 3, 3, 4. Now you can choose to multiply that by hand. So remember that would be first row times first column, first row times second column, second row times first column, etc. You can do it by hand or you can put it in your CAS. And you should find that that equals, leaving the half out the front, so if we answer part B, we're going to have to flip the solution around. So instead of going A inverse times B, this time we're doing B times A inverse. You can just take the half straight out the front. And then you can multiply those matrices again using CAS. And that time, if you did that correctly, you should find that that is equal to 1/2, 42 minus 34. Okay, so if you want, there's another example for question 11 here on page 374 of your textbook. It's quite good. So try questions 9 and 11 from 7.5. If you get stuck with question 11, have a look at that example.